Okay, so hi there folks, we're now in our next video in number theory, and in this video we're going to just reach the theorem 3.5 by the end. But before that, let's build some preliminary ideas. Okay, so in theorem 3.2 part 5, we saw that if A is congruent to B mod M, so if this is true, if A is congruent to B mod M, or mod N rather, then if we have some any C, for any C, if we're going to multiply C to the left hand side of the congruence and C to the right hand side of the congruence by the same modulo, there the congruence is preserved. Okay, so that is, if this is true, if A is congruent to B mod N is true, implies that C times A, or A times C, is congruent to C times B mod N. Now, the thing is, the converse does not entirely is not entirely true for all cases. The converse fails to hold. So, as a very simple example, 2 times 4, that is 8, is congruent to 2 mod 6. So 8 minus 2 is 6. So very simple. But whereas if we're going to combine them, 2 times, if we're going to cancel, I mean this 2 here, which serves as our C. If we're going to let C as 2, so 4 is not congruent with 1 mod 6, because 4 minus 1 is 3, which is not a um I mean, it's not divisible by 6, or 6 is not a factor of 3. So therefore, the converse is not entirely true. In brief, in short, one cannot unrestrictedly, one cannot unrestrictedly cancel a common factor in the arithmetic of congruences. So we cannot simply just cancel, just like in the arithmetic of equal equivalence, wherein we can cancel things provided they are common factors of the left hand side and the right hand side, right? But in the theory of congruences, we cannot do that strictly, okay? Or we cannot just do that um, wherever we want. So we cannot unrestrictedly do that. So, but with the suitable precautions, okay, take note, with suitable precautions, we can do the cancellation. One step in this direction, and a very important one, is provided by this theorem over here. So this is now our theorem 3.5. We're done with 3.1 up until 3.4. Let's have 3.5 right now. So let's put it here. Just a moment. Oops. Okay, there. So theorem 3.5 states that if C times A is congruent to C times B of this modulo n, then A is congruent to B, that is, we just cancel the C's here, provided our modulo is changed a bit, wherein it's now modulo n divided by D, where D is our greatest common divisor. Okay, again, let me fix this. If C times A is congruent to C times B mod n, then A is congruent to B, that's canceling the C's, mod n over D, where D is the GCD. So let's have a proof of this. Theorem 3.5. Okay, and let's try to put this here first. So by hypothesis, let's just hypothesize. By hypothesis, we can write, oops, we write more clearly. We can write something like this. So recall that here we have this one. So therefore, by the definition of the theory of congruences, we can fix this and we can write it like CA is rather CA minus CB, to check if they're congruent, is equal to N times a certain K. Okay, N times a certain K for some integer k. Okay, so take note, this CA minus CB can be factored out. We can get the common factor, which is C, and then write it as this. Okay, so far, so good. Okay, so knowing that the GCD of Cn is equal to D by our theorem, so mm, uh, knowing that the GCD, the greatest common divisor of C and N, is equal to D, which is stated here in the theorem. So there must be existing some relatively prime integers. So these integers must be prime integers. They're co-prime, relatively prime integers, meaning their GCDs are 1. I mean they cannot be the same. The prime integers R and S, satisfying this. So C is equal to um, this common divisor times R, for example. Okay, so meaning this common divisor here times R is going to give us C, and N is equal to, say, this common divisor times S. That's why S and R must be relatively prime, because C and N are different numbers. So thus R and S should be prime, relatively prime, and D is their common factor. So what we're going to do is to substitute these values. So um, by substitution, we have, so let's substitute it here. So let's take hold of this last part. So what we have is C times A minus B equals Kn for some k in the integers. Anyways, let's substitute the value of C as dr. So this will give us let's put it here. C is equal to dr, so we'll have dr times A minus B is equal to k, our n is equal to ds times ds. Okay. Um, no, let's put it here. And then let's try to simplify this. This will give us dr times A minus B is equal to kds. Notice in our left-hand side and the right-hand side, what we can do is cancel the d. This is where the cancellation for equality is, like I said, it's all true, because we can cancel something like this simply because they're the same with the left-hand side and the right-hand side. So if we're going to cancel that, this will be cancelled up. This will be cancelled up. Okay, so what is left with us is simply the r times A minus B equals ks. Okay, so therefore, um, maybe we can put it here. Oops. So therefore, hence, S, as clearly seen here, is a factor of R times A minus B. So it's clearly seen here because K times the certain S, or rather, S times the certain K will give us this product R times the quantity of A minus B. And also notice, as we have stated, that R and S are, you know, relatively prime integers. So we can say that their GCD of R and S is equal to 1. Now, by Euclid's lemma, Um, if um, you're not familiar with the Euclid's lemma, this is what it is stating. So the Euclid's lemma states that um, if A is a factor of if A divides B times C with the GCD of A and B. In a moment, let's put it down. With the GCD of A and B. Okay, let's put it here. With the GCD of A and B is equal to 1. Is equal to 1. Then it implies that A divides C. That is, we can cancel the B rather, since A is a factor of B times C with GCD of A and B equals 1. So therefore, if that's the case, we can just cancel the B and then we'll have A is also a factor of C. So that's the Euclid's lemma. We're going to apply it in this equation here, in this given statements. Okay, or specifically here. So if we're going to apply the Euclid's lemma there, okay, so so we have we can imagine this is one factor, this is another factor, and this is K and this is S. Okay, so we have that if um, S is divides R times A times B, and we know that that S and R have a GCD which is 1, so therefore we can say that S also divides A minus B. So S divides also C. So that is S divides A minus B, which may be recast, um, which can be written as which can be written as A divides B mod S. Okay, that's very clear, I think. A minus B is just equivalent of saying A is congruent to B mod S. So in other words, that is, we say that since we have an S here, we say that A is congruent to B mod N over D, N over D. Okay, since where did we get this? Where did we get this? Sorry. Remember that, try to remember that N is equal to ds. N is equal to D times S. So since because N is equal to ds, thus by by transposition, we can say that S is equal to N over D. Or we can write this as N over D. Okay, so therefore, this is the end of the proof. Okay, so that's it for this video. Thank you very much for watching. Hope that you would like and subscribe. Yeah, thank you very much. There are flying cockroaches here. Okay, sorry for that. Thank you.